If there's one rule that's practically universal in astronomy, it's this. You can only observe the parts of the universe that your instruments are sensitive to. As a result, when most of us think about the objects that are out there in the cosmos, we think about the components that are easiest to see, things that are bright, close by, and that emit radiation in the form of visible light. When we think of galaxies, we think of the stars within them. When we think of stars, we think primarily of the ones that appear brightest to our eyes and in our telescopes. But there's a whole universe out there to explore, and much of it doesn't emit any visible light at all. But when James Webb's remarkable, unprecedentedly sharp and powerful eyes peer deep into deep space, it opens a new window into the distant universe. From breathtaking sights to breakthrough science, our best tool is pulling back the shroud on the earliest galaxies, revealing the early universe is not quite like how we might have predicted. Join us as we dig deep into how James Webb's latest discovery just unveiled more secrets about ancient galaxies nobody knew. The galaxies we see today, even the earliest, most distant ones, are already old. They're massive, they're huge, and they're full of a variety of stars. For the most part, there are lots of heavy elements in there. Approximately 1 to 2% of all the atoms present in most galaxies are composed of materials other than hydrogen or helium. That's a big deal, considering that the universe was born without carbon, nitrogen, oxygen, silicon, sulfur, iron, or practically any of the elements we find in stars and galaxies today. It was 99.99999% hydrogen and helium to start, but that's down to 98 or 99% by today. But it's had billions of years, and many, perhaps an innumerable amount, of generations of stars that lived and died previously to bring the types of galaxies we're observing, complete with the variety of stars and stellar populations we find within them. If we look back to the distant universe, we also look back in time and find that galaxies were vastly different back then from how they appear today. They were smaller, bluer, more numerous, and poorer in these heavy elements than the galaxies we have today. Over the history of the universe, galaxies have evolved substantially. But how did the very first galaxies form? And what was the universe like when they first arose? The cosmic story that brought them to us saw a number of important steps happen first. Matter won out over antimatter, atomic nuclei, and then neutral atoms formed. The first generation of stars were born, died, and gave rise to the second generation of stars. But even after all these steps, there were still no galaxies around. Why's that? The simple reason is the smallest volume, cosmic scales gravitationally collapse first, while the larger scales take longer. Let's think about two important factors at play here: gravity and the speed of light. Gravity is the only mechanism that can bring ever larger and larger clumps of matter together. It's limited, however, by the speed at which things can gravitationally grow, and it only propagates at the speed of light. Given that the universe as we know it began a finite amount of time ago with the hot Big Bang, and that the speed of gravity propagates at a finite speed, it makes sense that the overdensities on small cosmic scales would collapse first, making stars the first things that form, while larger scales take longer, amounts of time for gravity's influence to dominate. Imagine you start with a small mass, a clump of matter that rises by some amount over and above whatever the average density happens to be. If you have some additional mass for it to attract, that's a light year away, it will take that matter an entire year to feel the force from the mass, since the gravitational force only travels at the speed of light. But if there's an additional mass 100 or 1,000,000 or 1,000,000,000 light years away, you have to wait for all that additional time to pass. Gravity isn't instantaneous. It only travels at the speed of light. So, what happens when you finally get a large amount of mass together in one place from the gravitational collapse of your first stars and star clusters? Well, they attract one another and can finally do so effectively. But the timescale for one massive star cluster attracting another is going to be much longer than the timescale for individual star clusters to form. Instead of looking at volumes of space that might be a few tens, hundreds, or even thousands of light years on a side, the scale of what might collapse to form a star cluster, you need to look on scales tens to hundreds of times as large to bring together enough matter to start to make the first galaxies. Remember this fact as well, that the original overdensities that lead to both star clusters and galaxies are only one part in about 30,000, meaning that these overdensities need to grow over large amounts of time. If it takes gravity tens to hundreds of times as long to propagate between star clusters than it does for gravity to propagate within an individual cluster, you might worry that it would wind up taking tens to hundreds of times as much time to make galaxies as compared to how long it took to make the first stars. Luckily, this isn't true. That's an overestimate. The amount of time it takes to create galaxies is indeed longer than the amount of time it takes to make stars and star clusters, but not by nearly that severe of an amount. The power of an attractive gravitational force is cumulative, so it's basically like starting a clock on a delay. The star cluster clock starts a few million years after the Big Bang. The galaxy clock begins perhaps 10 million years after that and starts with a handicap. It has farther to go to collapse. But this is okay. This is simply how structure formation works in the universe as we look to progressively larger cosmic scales. At the start, we have density imperfections existing on all scales, and they grow as soon as enough time has passed for gravity to begin attracting matter that's located a certain distance away. We form the first star clusters quickly, after perhaps 50 to 100 million years. We form the second generation of stars almost immediately after, in another 5 million years or less, because the first generation of stars lives and dies so fast, and the material ejected back into the interstellar medium triggers a new generation of stars to begin forming shortly thereafter. However, we then have to wait several tens of millions of years after those polluted stars form for the first galaxies to begin to take shape. The reason is that in order to make galaxies out of these star clusters, those early star clusters must attract one another across the abyss of empty space until they finally draw one another in so that they can merge. And it requires even longer timescales for large galaxies and then galaxy groups and galaxy clusters to arise. In this sense, structure formation in the universe is a process that we call hierarchical. Observationally, the hardest challenge when it comes to finding these first galaxies is that there haven't yet been enough stars formed throughout the universe to ionize all the neutral atoms in intergalactic space. So, as long as protons and electrons remain bound to one another, they behave as neutral atoms, which block and absorb light, particularly visible and ultraviolet light, which is a property that astronomers call extinction. The more neutral matter you have, the more efficiently your starlight gets extincted, which makes it all the more difficult to observe the light that's being emitted behind this thick curtain of light-blocking material. These conditions will remain until the universe is flooded with enough sustained ultraviolet light to permanently kick those electrons off of their atoms. This means that so long as the light from the first stars and first galaxies gets absorbed by those atoms, the universe remains in an opaque state rather than a transparent one. The earliest galaxies we've ever seen through James Webb's razor-sharp eyes date back to as little as 320 million years after the Big Bang, and these most distant galaxies were only discovered because they are both located along a serendipitously more ionized than average line of sight, and also because we're observing them at long wavelengths, where the emitted ultraviolet light gets stretched and redshifted well into the infrared portion of the spectrum. To be honest, the view of the ancient universe revealed by James Webb, our most powerful observatory ever launched, is so spectacular, but it's also too unexpected that scientists think it might pose a fundamental challenge to our basic understanding of the cosmos. The telescope has glimpsed inexplicably massive galaxies that formed some 500 to 700 million years after the Big Bang, leaving researchers baffled about how such galactic behemoths managed to emerge so early in cosmic history. The existence of these galaxies may present a serious challenge to the standard model of cosmology, also known as the lambda cold dark matter model, which is an extremely well-corroborated framework that accurately predicts many phenomena in the universe. Scientists call James Webb Galaxies cosmic rule breakers. This discovery sheds light on how early galaxies evolved and the fundamental processes that shaped the universe as we see it today. To discover the truth about these cosmic scofflaws, a team of astronomers used the Webb telescope to gaze over 12 billion years back in time and observe galaxies, as well as the rules they followed through cosmic history. The crew found that the same set of rules continuously prevailed, connecting the rate of star birth to galactic masses to chemical compositions. But these rules traced only so far back. The earliest galaxies defied them. As Claudia Lagos, an associate professor at the University of Western Australia, said in a statement, "It was like the Galaxies had a rulebook that they followed." But astonishingly, this cosmic rulebook appears to have undergone a dramatic rewrite during the universe's infancy. The most surprising discovery was that ancient galaxies produced far fewer heavy elements than we would have predicted based on what we know from galaxies that formed later. This disparity hadn't been spotted before because instruments used prior to James Webb hadn't been powerful enough to see the chemical makeup of galaxies as far back as around 11 billion years ago. However, the Webb allowed this team to look back to just a few 100 million years after the Big Bang, which showed a break in the relationship between star formation, mass, and chemistry. As told, when the universe first began to form the first stars and galaxies, it was filled with hydrogen and helium, the two lightest elements, with the former being the most dominant by far. Only a smattering of heavier elements, which astronomers call metals, existed until the first generation of stars forged them at their hearts and then dispersed them through the universe at the end of their lives via massive supernova explosions. This material was eventually incorporated into the next generation of stars, meaning these stars, and thus the galaxies they sit in, had a higher concentration of metals, a measure called metallicity. That process of metal enrichment has continued throughout the entire 13.8 billion years of cosmic history, meaning early galaxies are indeed expected to have lower metallicities than their modern counterparts. But even factoring this in, the team found that the metallicity of early galaxies was still lower than expected, much lower. And according to Lagos, their chemical abundance was approximately 4 times lower than anticipated based on the fundamental metallicity relation observed in later galaxies. The team suggests the disparity may exist because galaxies just a few 100 million years after the Big Bang could still be intimately connected with the intergalactic medium, the wispy hot gas and dust that exists between galaxies. The early galaxies continually received new, pristine gas from their surroundings, with the gas influx diluting the heavy elements inside the galaxies, making them less concentrated. As such, Webb's findings could challenge current models of galactic evolution and the mechanism that facilitated the development of the first galaxies. Interestingly, not only unlocking the secrets of the first galaxies, James Webb's newest images also has just delivered unprecedented insights into the life cycles of stars within these spirals, like never before. For a long time, whenever we looked at a large, massive spiral galaxy like the Milky Way, we assumed that what we could see, the stars, lined up with where the mass was. After all, in our solar system, the most luminous object of all, the Sun, makes up some 99.8% of the entire solar system's mass. But it turns out that's not true for galaxies. Stars represent only about 2% of a galaxy's total mass. Most of a typical galaxy's normal matter is in the form of gas, dust, and plasma, with stars only making up a fraction of atom-based normal matter. Meanwhile, the majority of a galaxy's overall mass is made of dark matter, a substance whose gravitational influence can be detected, but that leaves no absorption or emission signature anywhere across the electromagnetic spectrum. If you want to understand the life cycle of stars, you can't simply look in visible light alone, but rather need to examine the presence, distribution, and features of normal matter beyond merely the luminous stars. You need to understand the gas within the galactic disk and how it clumps up in arm-like configurations as density waves ripple through it. You need to understand how waves of star formation occur throughout the galaxy, from the central bulge all the way to the outskirts, as well as how gas gets funneled from one location to another. And you also need to understand the process of feedback and stellar death, where energetic light, winds, and even shock waves of matter from living and dying stars impact the matter within not only the spiral arms, but the greater galactic disk. That's the scientific motivation for why we'd need James Webb. Our best tool can image in both near-infrared light and mid-infrared light to achieve high-resolution views of the stars, gas, and dust within these galaxies. As you can see even from a visual inspection, the same dust that leads to the formation of new stars and that lines the arms of spiral galaxies doesn't block our view of the luminous sources in infrared light, but rather shines brightly of its own volition. As starlight strikes the dust within a galaxy, it heats up, but not to a hot temperature in the conventional sense of the word, but rather to temperatures that are hot only in comparison to the deepest depths of intergalactic space, just tens of Kelvin above absolute zero. Yes, dust does indeed trace the spiral arms of these galaxies nearly perfectly, revealing the most intense regions of new star formation within these galaxies. When you find a galaxy with a prominent bulge of stars, it glows bright in the infrared, a hint of central activity within the galaxy's nucleus, and potentially even an active supermassive black hole. Shells of overlapping material will glow brightly in infrared light and are driven by recent episodes of star formation. And many pockets within the dusty arm-like regions can be seen in a variety of galaxies, representing regions where recent episodes of star formation and stellar cataclysms, such as supernovae, have blown any remaining dust away. But perhaps most remarkable are the intricate filamentary networks of gas and dust that line these dense, arm-like structures within these spiral galaxies. Whereas the gas in most galaxies is made up of bare atoms or simple molecules and ions, normally just 2 or 3 atoms bound together, often with 1 or 2 electrons either added or subtracted from their neutral state, dust is far more complex in its structure. Dust can be large grains of material, from micron-sized up to the size of a few millimeters or even more, or it can be composed of extremely heavy molecules, such as carbon-rich organic molecules like polycyclic aromatic hydrocarbons. Where you have dense molecular gas, dust will be present. As density waves travel throughout a spiral galaxy's disk, the spiral arms themselves become the regions where that gas and dust are densest. When you have dense molecular gas in the presence of nearby young stars and star clusters, the dust within that molecular gas gets heated and becomes easy to see with a telescope like James Webb. And most recently, the Webb telescope's remarkable, unprecedentedly sharp and powerful eyes has just looked at 19 nearby, face-on spiral galaxies, uncovering the life cycles of stars within them. From breathtaking sights to breakthrough science, here's what was revealed when we took our greatest look of all at these nearby Milky Way analogies. With exquisite James Webb maps of the gas and dust with both near-infrared and mid-infrared data, this picture is not only confirmed, but we're learning all sorts of new details about how it happens inside the environments of these various spiral galaxies. The near-infrared imaging from James Webb has allowed astronomers to identify literally millions of individual stars, as these galaxies are close enough and large enough that Webb's optics can identify, resolve, and pick out enormous numbers of stars even at distances of millions or tens of millions of light-years. What James Webb is showing for the life cycle of normal matter and for the stars that form inside these galaxies is a remarkable story that not everyone anticipated. Whereas the conventional wisdom, for a long time, held that stars would form continuously along these spiral arms at all radii from the galactic center. Equally, the data is telling a different story. It appears that galaxies grow and star formation propagates from the inside of a galaxy on outward. Episodes of star formation appear to begin at the core of a galaxy and spread along the arms of the galaxy thereafter, propagating outward. We can see evidence for this by measuring the ages of the stellar populations we're finding at various distances from the centers of these galaxies. The farther away a star is from the galaxy's core, the more likely it is to be younger. On the other hand, if you look near the cores of many of these galaxies, you'll find, in Webb's images, that there's an emptiness of gas and dust there, and simply a dense bulge of stars, which generally tend to be populations of older stars. Additionally, where you see these bright spikes emerging from a galaxy's center, which a few of these galaxies exhibit, that is evidence for either a supermassive black hole that's actively feeding at their cores, or alternatively, a series of star clusters that are so bright that the image itself becomes saturated within James Webb's detectors. However, what's most amazing to many is that despite how different these galaxies appear from one another, both at a cursory level and in detail, is that the same processes are at play within them, and the same conclusions can be drawn from looking at all of them together. When we see these bubbles and cavities in the dust, as well as the filamentary dust network and how it follows and lines the spiral arms, we're probing the star formation cycle on the smallest observed scales ever. As astronomers measure the spacing between the stellar, gaseous, and dusty features within these galaxies, they're learning how a galaxy's gas and dust are distributed, which provides insights into the processes that shape them. From supermassive black holes at their cores to the star-forming events, both past and present, that are occurring within these galaxies, as well as the young populations of new stars and star clusters that have resulted from relatively recent star-forming episodes, James Webb is shedding new insights on how galaxies grow, how gas and dust are transported, and how star formation shapes the internal structure of these galaxies themselves. There's enough information encoded in these images that we can expect scientific insights to keep arriving from this study alone for many years hereafter, with better data and insights as to the vital factors that shape these galaxies. Simulations of individual galaxies should improve, enabling us a better understanding of how stars, gas, and dust are all interrelated, and how they impact the overall galaxy and its evolution as a result. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.